Okay. Good morning. Today we will discuss the second module which deals with bending moment and shear force in statically determinate beams. So this is a very important topic which is useful in designing any structure. Whether you are designing a beam or a column or a slab, so we have to calculate or we have to get the information about the bending moment forces and the shear forces at different sections of that beam or column or slab. Then only we can start designing the particular component of the building. So here the thing is statically determinate beams. Statically determinate beams means the unknown reactions and internal forces can be found out only by using equilibrium equations. You need not use any other equation. So you know equilibrium equations in the case of a two-dimensional structure and a three-dimensional structure. So you have learned that in mechanics. So equilibrium equations normally it will be in a two-dimensional structure, it will be 3. That is sigma fx0, sigma fy0, sigma m is equal to 0. So using those 3 equations we can find out the unknown reactions and the internal forces. Then such types of structures are called as statically determinate structures, and of course here in this module we are discussing about only beams, statically determinate beams. In that mainly we are going to have 2 types, one is simply supported beam, another is cantilever beam. In the case of simply supported beam, as you already know, the beam is supported at 2 simple supports like this. So at each support you have one reaction. So here RA and RB, they are the reactions developed in the beam due to the externally applied forces. Here I have taken W1, W2, W3 as the forces here. So forces can be any type. It can be concentrated load, it can be UDL, it can be triangular load, trapezoidal load, it can be external couple, anything it can be. So due to the effect of these loads, the axis of the beam, whatever I have shown here, this horizontal line, axis of the beam, this will bend like this. So that is the bending effect of those vertically applied loads. So you can see here all these forces are called as transverse forces because they are acting perpendicular to the axis. So once you find the reactions using these equilibrium equations, then we have to calculate 2 important things called, one is called as the bending moment, another one is called as the shear force. So bending moment means, so as the axis bends like this due to the effect of these forces, so if you take any 2 points C and D on the beam, so I have taken here C and D on the beam, so these points will be shifted to C dash D dash. This deflection is very small, so you cannot see that, it's very minute. So whatever these deflections will occur only due to the development of this bending moment. So there will be moment developed due to bending of the beam. That moment is called as bending moment. So here at C you have a bending moment MC, at D you have a bending moment MD. So both will be acting like this. That means both the moments they are trying to push the axis of the beam downwards like this. So axis bends downwards here. Such a type of bending moment is called as sagging bending moment, and in the analysis we take sagging bending moment as positive. So MC and MD, they are the bending moments at C and D, that is the flexural effect of all the forces acting on the beam. And similarly you will be having shear force like this. One shear force, if it acts like this, another shear force will act in the opposite direction, C and D. Suppose at C, if it acts upwards, here I have to take downwards. So there, that shear force is nothing but the transverse effect. Here I have shown the effect of shear force here, C and D. So the effect of FC is like this, they are acting like this. So this axis may get shifted here, C dash may shifted here. And here since it is acting like this D can be shifted to D dash like this, and this is your new axis of the beam. Just as an example I have shown here. So there are 2 effects here, one is bending effect, another is transverse effect. So bending effect can be determined by bending moment, transverse effect can be determined by shear force. So as all perpendicular to the plane. So this is the xy plane. So normally we take the bending moment as mz. So z is the axis which is perpendicular to xy plane, whereas shear force acts parallel to the cross sectional area. That we have discussed in the first module, how the shear force acts. Normal forces, that is tensile and compressive forces, they act perpendicular to the cross sectional area, whereas shear force acts tangential or parallel to the cross sectional area. So these two major effects we have to discuss in the case of a beam subject to different types of loads. So in the case of simply supported beam, this is how the bending effect will be, and we say that this type of bending moment is called as sagging bending moment, which we take it as positive in the analysis. And you can observe here, this axis gets deflected. Due to that effect, there will be an angular shift here. So that angular shift, if you draw a tangent here, the angle made by the initial position of the axis with the tangent at that point will give the slope or rotation. Here you will be having this theta A as the slope or rotation. At the same time, you have theta B here at this end. Similarly, you can have theta values at different sections of the beam by drawing the tangent and by measuring the angle. Now I will take up cantilever beam case. In the case of cantilever beam, you know that one end is fixed, another end is free. There is no support at the other end. So at the fixed end, there is no slope here. It won't rotate because there will be a reaction here. That reaction, that moment, reactive moment, MA, that will prevent the rotation. Here, in the simply supported beam case, MA value will be 0. So there is no moment here. And MB also will be 0. There is no moment here. Whereas in a cantilever beam, there will be a reactive moment at the fixed end and there is no reaction at the free end. There is no support, there is no reaction at the free end. Now in this case also, I have taken some forces W1, W2 like that acting on the cantilever beam. But in this case, what happens? This point won't deflect because of this rigidity and this takes a shape like this. So please observe the profile. So here in the simply supported beam, the deflection is like this, whereas in the cantilever beam, deflection is like this. So this type of deflection is due to negative bending moment. So we take this moment as hogging bending moment. Hogging bending moment, it tries to bend the axis upwards. If the bending moment tries to bend the axis downwards, it is sagging bending moment, which is taken as positive, whereas if it tries to bend the axis upwards, it is taken as hogging bending moment. Normally in general, so this simply supported beam is subjected to sagging bending moment, cantilever beam is subjected to hogging bending moment, but anyway, it depends on the type of load acting on the beam. Okay, so this is about sagging and hogging types of bending moments. Now we have to use sign convention. So in brief, we can, for doing problems, we can take like this. For bending moment, the sign convention is, so always bending moment is calculated at a particular point or a section. Now I have taken a section here. Xx is the section here, section xx. So here, if you want to find the bending moment at the section xx for this beam, so either you can take left side of that section or right side of that section. One side only we have to take to calculate the bending moment. If you take the left side of the section, if the force is upward, it causes a positive bending moment like this. So that is sagging bending moment like this. See here, this is the section xx, this force is acting like this. So to come to this axis, it has to come like this, clockwise rotation. So whereas if you take right side also, if you take upward force, it has to move like this, anti-clockwise. But here, both these two, they are giving sagging effect. So that is why, whether it is left side or right side of the section, upward forces give positive bending moment. That is the sign convention, that is sagging bending moment. And if the forces are downward, whether you consider left side or right side, it will give hogging bending moment, which is taken as negative. So this is how, very important. So sign convention is very, very important. Irrespective of whether it is left side of the section or right side of the section. So upward forces give positive bending moment, downward forces give negative bending moment. Similarly, shear force sign convention is like this. In the case of shear force, once again, if you want to calculate the shear force at any section xx, either in simply supported on cantilever beam. Here also we have to take any one side of the section, left side or right side. Here we should be careful. There is slight difference here. Upward forces, if you take left side, upward forces are treated as positive, downward forces are treated as negative. Whereas if you take right side of the section, downward is taken as positive, upward force is taken as negative. Please note that in the bending moment case, we have to calculate the moments, whereas in the shear force case, we only forces we are going to use. So now we can define bending moment at any section. So at any section means mx, at any section xx, okay? It can be at any point. So how to define that, how to find that, it is nothing but the algebraic sum of moments of all forces, including reactions. So reactions also should be included, acting either left or right side of the section. So any one side we have to take. Suppose if you are calculating the bending moment by taking left side forces of the section, some value you are going to get. Right side of the section also if you take, you should get the same value. That is a check. So at a section, for example here in the section xx, if I calculate the bending moment at xx by taking left side of the section, whatever value I get, you should get the same value by taking the forces acting right side of the section also. So that is check, okay? So that is how we have to calculate the bending moment. Shear force at any section, normally it is denoted by Fx. It is given by algebraic sum of all the transverse forces. So already I have told, transverse force means which acts perpendicular to the axis of the beam. That is transverse force, like this. This is the axis, this is transverse force. So algebraic sum. So how to take algebraic sum? This is the sign convention. If you are seeing the left side, upward positive, downward negative. Right side, downward positive, upward negative. This is sign convention we have to follow. Now, acting either left or right side of the section. Here also we have to consider any one side. Now, just to understand, I have taken an example here without numericals. This is simply supported beam having simple supports at A and B. So, RA and RB are the reactions. These two reactions should be found out using equilibrium equations. So, in any problem of BMD and SFD, bending moment and shear force, first thing is to find the reactions using equilibrium equations. That we will discuss in next class. So, here I have taken some W1, W2, W3 as the concentrated forces acting on the simply supported beam. And suppose if I want to calculate the bending moment at two sections, x1, x1 and x2, x2, the procedure is like this. So if I want mx1 is the bending moment at x1. That is a convention. M I am going to use for bending moment, F I am going to use for shear force. Mx1 is the bending moment at this point. Now I will take left side of this section. So what is the bending moment now? So this RA is acting at a distance x1, let us say, and this W1 is acting at a distance x2. So all these values you will be knowing in meters in a numerical example. So if you want to write the bending moment at x1 by taking left side of the section, so this is the sign convention we have to follow. So left side upward positive, downward negative. So here RA is acting upwards, therefore bending moment will be positive. So RA into x1. So moment is given by whatever force is acting or reaction is acting multiplied by the lever arm. Lever arm means that distance from that point under consideration. So RA into x1 is positive, whereas W1 is acting downwards, so it is minus. Downward forces give negative bending moment. So minus W1 into distance is x2. So that is the expression for bending moment at x1 by seeing to the left side of the section. Left side of the section. Suppose if you calculate the same value of mx1 by taking right side of the section, then it will be, if you see right side, so this W1 is acting downwards, so bending moment will be minus. Right side also negative, downward negative. So minus W2 into this distance, then minus W3 into this distance from x1 only I have to take, plus RB into this distance. So that is the value. So both values will be same. At a section, bending moment remains constant irrespective whether you are going to calculate by taking left side or right side. Similarly, if I want bending moment value at x2, section x2, it is mx2, Now I am calculating using right side. You can take right side. Right side means here W3 is acting downwards, so therefore it is negative bending moment. So minus W3 into this distance x3, and RB is acting upwards, therefore plus RB into this distance is x4. So this is the value of bending moment at x2. Now shear force, if I want to calculate shear force at x1, fx1, by seeing to the left side, see this sign convention you have to use. Left side upward positive, downward negative. So that means RA only we have to take the forces. We should not multiply with the distance. Distance we have to multiply only for bending moment. So this RA is positive, W1 is acting downwards negative. So RA minus W1. That is the shear force at x1. Shear force at x2 by saying to the right side, it will be here right side if you are seeing downward positive, upward negative. Therefore it is W3 is positive, RB is negative. So W3 minus RB, that is the shear force acting at x2. So this is a illustration, simple illustration of how we are going to calculate the value of bending moment and shear force at any desired section in a beam. Suppose if you want the bending moment at C, at point C, see to the left side. Left side if you see, RA is there and this distance we have to make. Okay, RA into this distance. That's all, only one term. So if you want bending moment at D, then see, if you see to the left side, RA into this distance from A to D minus W1 into this distance from C to D. So that is the expression. So either you can calculate by taking left side of the section or right side of the section. So initially we take, normally when you move from this end, initially at initial points we are going to take left side. After crossing some point, then we can take right side and calculate. That will be easy. Okay, next we will discuss with the problems in the next class. Thank you.